let's get back to talking about conditional probabilities. I actually want to revisit the example that we wrapped up the last video with involving that candy box at my grandparents' house. Just as a reminder, the box has 5 coconut candies in it, 10 caramels, and then 15 with like a chocolate fudge thing in the center. Anyway, so I want to change the parameters a little bit. I described it last time in terms of my walking into my grandparents' house and grabbing a chocolate. So imagine instead that I walk into my grandparents' house and I see my cousin over the candy box, and she pops a candy into her mouth and is eating it. So customary greeting type stuff, and I recognize the candy box and ask her excitedly, "You didn't take one of the caramels, did you? You know those are my favorite." They actually would have been of the 3 options we have here. And she doesn't answer me. She just has this sort of devilish grin on her face, and then she walks off. So now I'm curious how likely it is that I can grab a caramel out of the box. So I'm not necessarily interested in how likely it is that they're both caramel. I don't care what my cousin ate, apart from the fact that it may change how many caramels I have available to me. So we're looking at this a little bit differently here. So we want the probability that our second candy is caramel, regardless. Don't know why I changed pronunciation there. I'll probably do it again. So anyway, so regardless of her choice, we want to know how likely it is that I get a caramel out of my second pick out of the box. So we kind of have to break this into 2 cases. First case, she did eat one of the caramels, and that means I have fewer to work with. So based on what we saw last time, well, there were 10 caramels in the box out of 30 total candies. So that means there's a 1 in 3 chance, a 1/3 probability, if you will, that she took out one of the caramels. Now, so how likely is it that I'm able to pull out a caramel now that she's taken one of them? All right, well, let's go back. So how many caramels are left in the box? 9. It's not too challenging to work that out. How many total candies are left? Again, she only ate 1, so we got 29. All right, and from what we saw last time, our product rule for calculating these probabilities, because we're working down the chain, says we need to multiply these together. So I'm kind of shorthanding this. This isn't precise mathematical terminology. I need to multiply these together. 1/3 times 9 over 29. If you have a decimal, that's okay. But it turns out this will reduce down to 3 over 29. So that's one scenario that's possible. It's not the only one, though, because there's no guarantee she took a caramel out of the box. She refused to tell me, the punk. Anyway. So, case the second. She didn't get a caramel initially. Well, however you choose to go about getting this, there are 20 candies in the box that aren't caramels. So we have 20 over 30. You could do it, using that 1 minus thing from a few sections back. If not, it's okay. So it turns out, kind of the odds are in our favor in that sense. There's a 2/3 probability she didn't grab a caramel. All right. So now, that means I've still got 10 caramels available to pick from out of a box that now only has 29 candies in it. Again, we're following down a chain here. That should say not NOL. So product rule again says we need to multiply these together. Again, if you went decimal, that's okay. I said, yeah, I'm comfortable with fractions though, so 20 over 87 is what I end up looking at when I deal with that thing. Okay, so we've got 2 separate results. The catch is, now what good does this do me? Is there some way I can combine these 2 guys together? And it turns out, yes there is. Because keep in mind, can these 2 things happen simultaneously? No, she only ate 1 candy. There's no way she got one that was both caramel and not caramel in one pull from the box. As such, these are mutually exclusive, right? And what did we find out about mutually exclusive, events and their probabilities? We can add them up. So I can take these 2 guys here and add them together. So I have 3 over 29 plus 20 over 87. Again, decimals are fine here. Oddly enough, you're going to end up finding out when you work this out that probability if you didn't do any rounding off, is 1/3, which is kind of wild in this context. It ends up making us think, if you go back, that's exactly what the probability would have been if I'd been the first one at the box. Without that piece of information, I basically have to act like like there's still 30 caramels in the box. I just can't happen to pick that one. So, interesting. All right. So, the idea is fairly straightforward. We use our product rule to multiply together chains in these scenarios. Then the chains are, by definition, mutually exclusive, so we can add them up. As it turns out, there's a relatively neat way to visualize this that we've kind of ended up, talking through before. So bear with me for a sec. I need board. That's better. Okay. So the way we're going to be able to visualize this is something that we talked about way back when we were dealing with counting stuff toward the beginning of the course. We can generate what we call a tree diagram to demonstrate exactly what's going on here. So what I'm going to do is kind of draw some branches, like so. So representing my cousin's pick out of the candy box. Maybe she got a caramel. Don't know why I wrote an M, but caramel, not. All right, we worked out the probabilities of this happening, right? So we had a 1/3 probability this was her choice, and then a 2/3 probability that we didn't. All right, now time for my pick. The one that matters. All right, so maybe I got a caramel, maybe I don't. Down here, same thing. All right, so we can work out the individual probabilities that go into this. So from what we did before, in this instance, it was 9/29 that I grab a caramel, given that she'd already taken one. As it turns out, that left 20 non-caramels still in the box. So that's 20/29. All right, so down here, we had 10/29 for the probability that I get a caramel if she grabbed one of the others. And then here, again, the key thing to remember is that at any one of these branches, my probabilities for however many branches there are, I think all of our choices are like 2 splits. But the probabilities need to add to 1 because we want to cover all of our bases. So that would give me 19/29 down there. So again, at each set of branches, the individual probabilities you're labeling on the diagram should add up to 1. So if you're only given one of them, you can usually subtract from 1 to get the other. Okay. And to follow what we're doing, I was interested in this branch because I want to know how likely it is that I get a caramel at the end. Or I could follow down this branch. So these were my options that got me my delicious caramel candy at the end of my choice. So I've laid out in the PowerPoint slides kind of how you can utilize these tree diagrams. Label branches with probabilities. Each particular connected set of branches, the probability should add to 1. Additionally, if we make our way down here, we're following sort of a chain of successive events. That means we need that product rule thing for conditional probability calculation, so we multiply our way down here, and this would give us the 3/29 that we saw before, or the 20/87 that I got following this chain. So multiply down these chains if you're going horizontally. By design, each set of chains, or each chain rather, or set of branches, whatever you want to call it, is mutually exclusive of any others. So that means if you're combining the results of multiple branches, you can add them. All right, so that's the candy box. I wanted to take a look at maybe a slightly more practical example, but I'm in need of board again, so bear with me. All right, so imagine that we're working for some company that manufactures woozles. Just run with it. So we have 2 factories, one in the town of Pixley, another one in the relatively nearby town of Hooterville. The Pixley plant is the bigger one. It makes 65% of our woozles, which means only 35% are coming out of the Hooterville factory. Downside, the higher volume, apparently Pixley's processes aren't quite so sound. They have a 10% defect rate on their woozles versus the 5% defect rate in Hooterville. So the idea is these go into some central distribution warehouse or something like that, and they end up getting mingled together, so we don't know which are which. Imagine we're some sort of quality control person, and we're sampling to see what the overall defect rate is. Well, how likely is it if I pull out a random woozle without knowing which factory it's from that I'm going to get one that's defective? So that's what I'm after, the probability of picking out a defect. All right, I'm going to have to erase one more time that I've got these things sketched up, so bear with me as a tree diagram is going to appear out of the ether. Okay, so here's what our tree diagram looks like. We've got two choices. Which factory does this thing end up coming from? And given, once we know what factory it's from, is it defective or not? Okay, so we've got to convert our percentages from that table into decimals. So we got 0.65 for our Pixley, percentage. Same thing for the Hooterville, it's 35, becomes 0.35. Our defect rate up here was 10%. That means that if 10% are defective, that means 90% aren't. So we have 0.90 right there. 0.05, goes 5% defect rate coming out of the Hooterville plant. 0.95, there's a 95% chance we don't get one that's defective. All right, we want to follow the branches that lead down to a yes. So it's actually the exact same picture from before, right? So, maybe I should rethink this. Anyway, so we need to work our way down each of these branches and then add up the results. So we have 0.65 times 0.10 here. Coming down through this one, I've got, writing out extra stuff I don't need. Well, yeah. All right, so, following down the chain, multiplying, you can work those guys out. So the full defect rate now, since these are separate branches, I can add up the results. So 0.0, if I multiply these two together, I should get 0.065. This one, if I work out that product, I should get 0.0175. So then when I add, I get 0.0825. Or if you want it as a percentage, which your bosses probably would, your defect rate overall looks like 8.25%. So that's what I want to talk about as far as conditional probabilities go. So we've got one more section of material I want to take a look at. It turns out it's not quite as intense as what we're dealing with right here. It's weird. It comes later, but I think the calculations and stuff that you see will actually flow more directly. So stick around.